This is section 8.10. In section 8.10, we talk about an interesting reaction called anti-dihydroxylation. In this type of reaction, you have some alkene, and you treat the alkene with some peroxy acid, RCO3H, instead of CO2H. Remember, carboxylic acids are typically CO2H, but in this case, a peroxy acid means it has one extra oxygen. That's why we call it peroxy. So it has 3 oxygens, CO3H. So you run this reaction in the presence of acid, which is why we say the hydronium ion is there. And what you end up getting is anti-addition of 2 hydroxyl groups. Notice that one is red and one is black to signify where each of the oxygens came from. And the mechanism for this reaction is shown here, where you start with the alkene, and the alkene attacks one of these oxygen atoms because it has a partial positive charge. Once it attacks the oxygen atom, an interesting rearrangement takes place where you can see that there are 1, 2, 3, 4, 5 atoms here in kind of what could almost look like a ring. Well, upon attacking one part of that kind of ring, the electrons will flow around to make a new product, this acid here, because the oxygen-oxygen bond flows down to the oxygen-carbon bond. And since that carbon would have 5 bonds to it, the electrons that form a CO double bond then come over and take the hydrogen. That way, it relieves that 5 bond pressure here on the carbon, but then the hydrogen would have 2 bonds, and that's just as bad as a 5 bonded carbon. So the electrons from the OH bond then come down and make a 3-membered ring with the other carbon on the double bond molecule here. And what you end up with is this epoxide. That's what we call a 3-membered ring with 2 carbons and 1 oxygen. It's an epoxide. And this epoxide then can be protonated by the acidic water that we had. Remember, H3O plus was also present. So the epoxide can be protonated by the H3O plus. And so we're going to come here now. So here, the protonated epoxide now also has a positive charge, just like the bromonium ion and just like the mercurinium ion had. And just like in those reactions, the oxygen in water will attack the other face of the double bond to give this oxonium ion, which can be then be deprotonated by water to give the anti-addition product of the dihydroxylation. And remember as well that acidic water is still regenerated from the last deprotonation, and we have this acid molecule that was from the epoxide formation. And the types of peroxy acids that we typically see in these reactions are only 2 normally. Either the most famous one called MCPBA, it's called metachloro peroxybenzoic acid. It's something you'll encounter later on in CHE 232, but for now we'll just call it MCPBA, or peroxyacetic acid. Either of these can be used to make the anti-dihydroxylation go forward. So this was section 8.10.